Okay.
Oh, do I need to record it?
I've just pressed it already.
Yeah, sorry. No.
So, the seminar. So it's a pleasure to introduce this week's just speaker. So our speaker is Professor Chris Johnson from University of Utrecht. So Chris is an associate professor of human AI interaction, specializing in mobility. He's at the Division of Experimental Psychology in Utrecht University, and he's also the co-director of Utrecht AI and Mobility Lab. So we're looking forward to your talk. Chris is also here tomorrow for Tom's Viva. So he'll be around if you have any, if you want to have further.
The main reason I'm here.
Later today or tomorrow. Right? So yeah.
Great, thanks for the introduction. You said most of what I wanted to say with this slide. It's a pleasure to be here. It was good reading Thomas's thesis and looking forward to a great discussion tomorrow. For today, you are an HEI group, but I'm in a psychology group, so I sometimes need to argue why we need HEI. So some of that will be part of it, even though you're probably already convinced. But I want to show why thinking about human automation interaction or human AI interaction, if I'm talking with my AI mobility hat on, why that's interesting in mobility and where there's opportunities. So automation has actually been around quite a while. One of the ideas is that the Ford factory assembly line is one of the starting points of automation. And this is automation today. I don't have sound, I think. Oh, I do. Oh, on my laptop. Well, sound's not important for this. What you should pick up from this is today's environment, but there's lots of humans actually, and I hope that this is not a surprise to you that even that despite that AI and automation is making tremendous advances, that there's actually humans in all these situations, even the one maybe studied most. Factories. In Utrecht is one of the major train hubs of the Netherlands. If the train station in Utrecht is down, almost the entire country is down. So we do some work on trains, and there has also been automation from physically sort of next to the track, making the track change so you could drive the train somewhere else, towards controlling it from a remote switchboard. I saw this somewhere in a screen. Does anyone know how I can remove this? Make this go away?
You can drag it to the edge of the green bar.
If you click on more,
yeah.
Okay, and then hide floating meeting controls.
Thank you. We're technically not allowed to use Zoom, but anyway, that part needs to be cut from the YouTube. No. So this is already some remote work, right? Some form of automation that you don't have to do the physical labor at the tracks. And oh no, I'm not in PowerPoint. Today's train operation is remote. This is not a train operator, but my PhD student posing picture I can use all the time. And now a lot is automated, and automation in the trains is useful in the Netherlands because we have quite a dense network of tracks, high volume of trains. In order for it to work when there's something going wrong, AI can assist to make sort of these last minute recommendations that are difficult for a human train planner to do. But that's the future. Nowadays, still humans are operating it. But even in a system where there's automation, there's the actual human, the planning, which could be made by human and or machine together. The path of the train drivers, those are humans. And there's other screens where they also interact with humans. So even in this situation where theoretically there could be a lot automated, there's humans. Well, why do we even want to automate? For different reasons. One reason you see a lot is that we want to get rid of human error. And we know that particularly from the automotive domain, right? that in 90% of traffic accidents, there's some driver-related factor involved, which can be road rage, arguing with the person next to you in the car about which turn to make. I think we've all been there. But it could also be that you're a bit sleepy or that you're distracted by your phone. So wouldn't it be great if everything was automated? Like this. Now I don't hear the sound. I don't know what the origin of this paper is. Isn't it wonderful? I think not. I would be very scared if I was that pedestrian or that cyclist walking over there, but theoretically, this is very ideal, right? At least there's a continuous flow of traffic. Behind some of these ideas, well, we're not there yet that it works like that. So in current systems, human and automation are interacting like in the Tesla. The car does a reasonable job in staying in the lane and remaining distance to the cars in front of them. But you as a human driver need to be like this driver, hands ready to grab the wheel if it's needed. And that's great in theory, but this is typically practice where people are distracted by other tasks. And particularly if automation in the car improves, well, even without the automation, we're already being quite distracted by tasks. Estimates are quite difficult to make for naturalistic driving, but I think 10% of the times. As automation increases, people want to do even more tasks. Take a nap, come home while having being drunk because you went to a party in the city. And where does it go? Where it goes wrong is that in the design of these systems, there's some conceptual idea, which I trace back at least to the 1950s, which is called the FITS list, or as it's nicer, MABA, men are better at, machines are better at. And the idea is that we as humans are great. We can detect things, we are great at perceiving, we are good at making judgments, we can improvise, and we have good long-term memory, and machines are great. They have good speed, they have power, they can replicate things, but they only have a short-term memory. Well, the way I introduced it already, you might already anticipate the clue. This is a bit stereotyping, I'd say. So humans and machines are no stereotypes and are not static in their properties. A automated vehicle that does really well on a highway at a reasonable speed, I don't know what that is in miles per hour, 60 miles per hour, might not function well maybe on the German highway at ludicrous speed, or it might not work well when you're driving through a situation where there's disruption, or if there's snow and your sensors are jammed. So it's not this clear cut as we originally thought. And the same holds for us as humans. Yes, we're great in making judgments, but we also know that we have biases. So some of our judgments are flawed. And how we act also differs on the context. So we also change our behavior in different circumstances. And what you then see in action is something that's known for a long time, which is the irony of automation by Lisanne Bainbridge. Over 40 years this has been known, but still in action, the principle, so that technology is introduced to solve something. So it can reduce or replace the complexity or capacity of the human task. So in the case of automated driving, wouldn't it be great if the car could stay in the lane, so we can, as humans, can pay more attention to the road instead of mundane stuff like staying in the lane and changing gears. So we get free capacity for other tasks. But in reality, it changes human behavior, and sometimes in unanticipated ways, and potentially making the task harder instead of simpler. So you see this in the automated driving. One of the motivations is to make it easier for me to see what's going on in the surroundings. But because the car is taking over tasks, maybe my mind starts to drift, or I find it more important to answer that email or message because the car is looking after itself anyway. So given that there's this weird situation where we do want to introduce the technology because it does bring things for safety, we still do need to understand human behavior and also changes in human behavior. And I think through an interdisciplinary lens is particularly needed, which for an HCI audience you are used to. And I think from a psychology perspective, but also from a fundamental computer science perspective, maybe you want to make predictions from theory. So you want to know what's something essential about human behavior and how does that apply to a new future situation. But you also want to understand things through observations in real life. That later part is not my classical training, but we're doing some of it. So I'm doing attempts. I'm sure some of you do better in situ work than I do. So with that motivation, I hope I briefly touched upon why we even want to consider human behavior in human automation interaction. I want to show examples of research. I'm going to mostly be talking about human vehicle interaction, as that's something that I know some of the researchers here are very interested in. I'll then spend some time on eye gaze by bridge and lock operators. And I'll only briefly touch upon two other projects, which are about modeling pedestrians in urban digital twins and trust in automation by train operators. So let's go to the automated driving scenario. So the ideal scenario is like this. You are in your car is taking over some task like staying in the lane, keeping an appropriate distance to the person in front of you. But if there's an alert, you are ready with your hands to intervene within a couple of seconds. This is called a transition of control. So some part of the control of lateral and longitudinal driving is on behalf of the car. They need to do it. But if the car can't manage or there's an unexpected situation, it's transferred to me as a human driver. The classical engineering perspective, I'd say, is that there's a stimulus, an alert, and an immediate response. And what you see in a lot of the research is that there's a focus on what's the time interval between the alert and the response, and how can we get that minimum? What's the minimum response time you need? Which is a very useful parameter, because we shouldn't design systems that function in such a way that there's even shorter time than the minimum amount of time that you need to require. What we did with some colleagues is look at, well, what can we learn from another domain? So interruptions, which you all know from when you're in your office or when you're doing dedicated work at home. You're working on something, your colleague walks in, or there's an incoming email alert. I hope you turned those off, but maybe you still have them on, turn them off. Or your phone goes. You want to respond to it, but you're also sort of in the middle of it. That's a situation that has been studied a lot. And we know that there's a pattern that you go through, and that can be applied to driving. Through such a lens from interruptions, you would say, well, maybe we're working on something else while the car is driving. So I indicated that with the hand that's on the phone here. Then at some point, the alert goes. And instead of immediately grabbing attention, what we know from the interruption literature is, well, maybe you don't immediately grab attention because you might still be in the middle of something, and immediately stopping keeps your workload high, makes you not that concentrated, can generate stress. So maybe you want to finish something, like finish typing a sentence if you would be in your office, or make a quick note where you were so you can pick it up later again. But you also don't want to continue working on that too long. So maybe you do take a quick glance at the road, like, well, what's going on? Should I immediately grab the wheel? Maybe not. Okay, I can finish where I was and then grab the wheel. So you go a bit back and forth, which I indicated with the blue arrows. Then you might grab the wheel. And later, there might be another phase where you've maybe handed over the control to the car, but maybe you're not that confident yet that the car is doing what you want. At least if you will be me, I always compare this with driving on the German highway. I've been in a traffic jam, and then the traffic jam is cleared. I'm still manually driving, but I'm not that confident the traffic jam might appear again. So I'm sort of in this state like, can I drive a bit more relaxed, or do I need to pay attention? That's my analogy for this phase, but Here it would actually be the car is driving, and I've allocated the tasks to them. But I also want to look back at the original task that I was focusing on. And again, I might go back and forth and try to build context. Where was I again with that email? And then continue. If you put this next to the interruption literature, you can identify 10 stages. You don't need to know the details of the stages. If you do want to know, look up the paper. But what's important is that by having these stages, you can make targeted interventions, whether it's for me as a psychologist sort of trying to understand what's the phenomenon that's happening here, or for someone who's maybe designing for an intervention at a particular time, how would I design for the intervention there? Instead of saying, I'm looking at takeover responses, you can say, I'm looking at the orientation stage to the road, which is stage 3. So it offers opportunities for targeted testing and interventions, and I want to showcase a couple very briefly. So the first is work of my former PhD student, Remo van der Heijden. And he was looking at very neuroscience-inspired studies of alert processing. So the idea is you're in a car. I'm soon going to play sounds, which might be loud online. So online folks, can make sure you can cover your ears if it's too loud online. Here it's hopefully okay. I didn't test it. The idea is that in the car, there's all kinds of sounds. So there's sounds from within the car that you hear frequently, and there's sounds from outside of the car, and some sounds that come from the environment. And we mimic that with a psychological paradigm called the novelty oddball paradigm, where you can hear constant tones. Here come the sound. I'm annoying if it's too loud. And those are very regular. Occasionally there's one deviating, and occasionally there's a sound like a dog, which maybe you need to do something with. And our question was, well, how does our brain respond to those other sounds if they're infrequent and in the context where you do occasionally hear information? So we had people in the driving simulator, and they would hear these sounds while they were really watching a video clip of a simulated drive, like pretending they were driving themselves. This one's really soft. We've done multiple studies on this front. This particular data is from this specific paper. If you're stationary, so not doing anything at all, not even driving, maybe it's a black screen or a screenshot. If you hear a unexpected novel tone and you calculate the difference in brain response compared to the response to a tone, so a difference wave, we find that in frontal regions of the brain, there's a stronger signal around 300 milliseconds after the sound is played, which it's called the frontal P3. It's some signal of a behavioral interrupt, like maybe your mind is preparing for you. You might have to do something. This is all interpretation of what the signal means. Very plainly, there's just a change in signal. There's some more activity frontal that you can do. If you are manually driving, that is severely reduced. Our interpretation is because you're concentrating on the driving road and you're doing the driving task. And the question is, well, what happens if you're driving an automated vehicle? Actually, there it's also reduced. If you would plot it in a different plot, which I haven't shown here to keep it simple, it's sort of in between automated drive, in between doing nothing, so really being susceptible to everything else, and manually driving, which is a problem because in these automated vehicles, the vehicle relies on you being able to respond to the alert. And I should say this is a quite controlled neuroscience study, so it is not like, oh, you needed to act on every signal. We really measured what was going on in the brain. We did look at situations where we combined automated driving with you also responding to other stimuli, to words, and then that susceptibility is reduced even more. So in a state where we are, where we need to respond to alerts, it seems like our brain doesn't always respond as good as we want to, at least by this metric. Another study was by Nabil Chi from the University of New Hampshire. Actually, I was fortunate to work with him remotely and join the team. And he looked at this interleaving phase, so the blue arrows. And that was presented at this year's AudUI. And the idea was if you're doing some task, some distracting task, in this case, it was a 20 questions game. So the experimenter had some concept in mind, and within 20 questions, you need to guess, what is it? Is it a living being? Yes, no. Is it a female? Yes, no. Is she known for music? Yes. Is it Beyonce? That idea. And they did very careful eye tracking of where attention was while you were doing this through a text interface. And then the question is, do people even interleave? We've claimed that in the theoretical paper, like that's what people might do. Do they do it? If you give them a bit more time, we gave them 10 seconds, which is longer than the typical interruption study does. If your priority up front is, if something needs to happen for driving, go for it. You need to do as good as possible. They're not very likely to go interleave. They'll switch immediately to the driving or relatively fast. If their priority is the non-driving related task, so if the 20 questions game is maybe not that interesting, but in real life, if that text message to your partner, like pick up the kid, I'm delayed, that is urgent to you, you have a higher chance of that you start this interleaving pattern. Still 20%, so the question is what's the magnitude? If you allow more time for takeover, you're at almost 50% if the non-driving task is your priority. Then you really continue a bit more with this interleaving going back and forth to the road. But also if driving is your priority, you're likely to do that. So they actually overlap a bit. I thought this was cool data. Now the next data is also really cool, but the way I could visualize it in this figure is a bit limited, so see through it. On the horizontal axis, you see when the interruption game, what part of the non-driving related task of the 20 questions task was I? Was I at stage 0? I'm about to start a new series of questions. Have I asked one question, 2, 3, 4, 5? The further you are, we actually got some instructions on how do you do this task. The further you are, the more likely that you can complete the 20 questions game. And then on the y-axis, you see at the moment where you really took the wheel, what stage were you on? Were you at the start, one question in 2, 3, 4, or 5? On the diagonal, you see behavior where people stay in the stage where they're at. I've answered one question. I've asked one question at the time the alert went off. But at the time where I grabbed the wheel, I also still only had answered that one question. I haven't done anything else, or 2, or 3, or 4, or 5. Then there's other behaviors. But this is the interesting part, the one highlighted in green. If I'm at one of the other stages, the further you are, the higher the chance that you'll finish at stage 0. What does that mean? I complete my task. So this is what I sometimes refer to as a natural breakpoint in the task. I finish what I'm doing, and then I continue on. Technically, it could also be that they even did 2 questions. Or 2 series of answers. I haven't re-looked at the data in that level of detail, but I thought that was quite interesting. So this is also something that the literature suggested and that we therefore predicted, like, oh, you'll be interleaving and maybe to finish for this natural breakpoint. And I think this is data that suggests that we're onto something. Other work that I was involved with but didn't do myself was by Michael Gerber, who was at Queensland University, but he's now in Germany in industry. And he looked more widely at a phase where you don't have to take control, but what do you even do? You have a question?
Mhm.
Oh, yeah, go ahead.
Yeah, so the time budgets that were given were 10 and 30. Did participants know the reason for the takeover or just merely the time?
Oh, right. So in the previous study, the time budgets were 10 and 30 seconds. Did they know the reason? I think they were instructed up front, but that they have more time. I think I'd have to look up the details.
No, I mean, like they know that they're taking over because like there's a child or like there's like what type of hazard?
I can't remember the details, to be honest. It was they did not, but they did not know what the hazard was. So they would have to build that context. Yeah, and look at the road to build the context. We'll need to look up afterwards and then we can discuss. Michael's work was looking more on the intervention side. So they had this really cool simulator, which I haven't seen in person. And Michael's been collecting data here in COVID time. So with 200 participants, like incredibly tricky. He had made a recording of a drive through Queensland and showed it to 200 participants. And they were, it's Australia, so they were also watching an Australian soap. And there was, while they were doing that, there were different interventions that could help them with maybe staying alert of what's on the road. So one concept was an uncertainty display, which he labeled angel wings. So the idea was that as the car would become more uncertain, we'll get to how it knows that in the simulation, the wings get spread out and the colors change. So there's a cue in size and there's a cue in color, like maybe you want to pay attention to the road, something might be coming up. And then it looks like this. So red might be a situation where you want to look at the road. And another concept would be an interruption. So it literally, the task gets taken away, which would look like this. Normally in that square, there would be this Australian soap. Check the environment. And then the question was, how do those interventions impact gaze behavior in the car as some proxy for situational awareness? The measurement was a drive through various parts of Queensland. This, if anyone has been there, it's this blue road. I haven't been there, so I can't tell you anything about it, except that that's a city part, a highway part, and a suburb part.
Kelvin Road.
So,
Kelvin is a very commonly used for streets. And
okay. I don't know. The car needed to know when it's uncertain. So one of these, let's see, can I click this away? They showed clips and then they had a slider. How stable is the road here? That was the metric for uncertainty. And they asked 18 automated driving experts, how do you rate it? And then they came up, PowerPoint. They came up with a score. So when it's low, it's, for example, when you're waiting for a red light, you have to pay attention whether the right light turns green if you would be driving, but if the automated vehicle is driving, maybe you don't. When there was a long left turn with dense traffic, maybe that's not a stable situation, so you might want to look at the road. And when the car is merging on the highway, maybe that's a situation to look at the road. And in this fashion, there were multiple parts where there could be something interesting. With that data, we're now going to see over time, what's the time, what is the percentage of, over the time, what is this uncertainty metric? And then there was a threshold that Michael said, like at this point, if you would be in the interruption condition, you would be interrupted. Otherwise, it would affect sort of the color and the spread of the angel wings. So when you're at the top, it will be wings spread out with red. In the baseline condition, you see a reasonable pattern. I think that when uncertainty, I don't know what's happening with the clicking. When uncertainty is high, the baseline condition, less participants look at the non-driving related tasks. So they look at the road. This is what you want. When uncertainty is low, so when it's relatively stable, more people look at the road. So the blue line is higher. If we then introduce the conditions, so if you have the uncertainty display, the angel wings, it's actually more or less the same. But when you introduce the interruptions, so you take some information away, that's when the people start looking more at the road, at position, even more people, because it's percentage, even more people start looking at the roads. And what is nice, is, I don't know what's with this automatic question. What's nice is that even in situations like here with the arrow, where there's no interruption anymore, there's some sustained focus on the roads. That's the main finding. Michael also did an analysis where he looked in a qualitative way at heat maps, which I can also show video clips of afterwards. So I think the driving part, what you could say is this interruption model. What was nice is that it's grounded in theory. There's some predictions that follow from it, and it helps to ask targeted questions and to guide both more experimental work and more design work. And I've highlighted some areas where I think we were on the right track. Of course, it's not magic, so we also weren't always right. And all these nuances are in Nabil's paper, for example, where people were really immediately switching to driving instead of interleaving that what we would have predicted. We also made a tool, which I only thought of during the flight, like, oh, I need to put the tool in because it's relatively recent. Recent that we published it. It's a R-Shiny app, and you can interactively play with parameters. There's some database that we got from another paper by Zhang and colleagues from TU Delft. We put the database in, and then we said, well, what would these different stages, what would the distribution of time potentially look like given the data that's been reported in the literature, mostly that one data set, but it has around 200 studies in it, really amazing. And you could change things like, well, what if we only look at studies that have an early alert onset or an auditory alert or a visual alert, and it will change the distribution. So my hope would be that this helps people with playing around a bit, like what might it be, or if you have your own data, you can put it in the tool and see what it predicts. I don't download it. You can download the code yourself, do it on your machine. So it's for the research community. There are a lot of caveats. Some things have not been tried in the literature. So if you then generate a simulation, it's based on one study, which is not really predictive. So you do have to be very aware of the number of groups that are included. So 260 papers reported stage 5, which is the grabbing the wheel. And you can see that those intermediate stages, few researchers identified them even, or we were able to distill them from their data because they haven't been the focus, those intermediate areas. That's the driving part. I want to shift gears a little bit and talk about work from Rutger Stuut, who is my PhD student. His day job is a human-computer interaction consultant at the Dutch Ministry of Infrastructure, at the Dutch Road Authority. And he needs to advise on how bridge and lock operators do their work. So the first study is done in that house, where these 3 locks, I only recognize 2, but there's 3 areas where you can go through with your ship, how they are being operated. And this is a massive amount of screens. If you look at it first sight, it's overwhelming. They've really taken their human factors on board and thought about the way they organized them. I was a lot more convinced that it's safe once I saw it in practice and had some more explanation, because the first time I'm like, oh my God, what's happening there? I'll talk about that a little bit. And in the long run, they want to change that. Instead of seeing individual cameras with the CCTV, that you have a stitched camera image. That's the technical question, which I am not solving because I'm not qualified to do that. But Rutger wants to provide them with human factors info. And the more theoretical question we have is, well, in this scenario, what kind of strategies do people even use with their eyes for as far as we can see it? And how consistent are they? And I'll only highlight a snippet of it, recently published. So here's again the operating room. There's a set of screens which show images of these, I don't even know what the English term is, but where the boats go. And there's 3 canals, so to say. The first one, the second one, the third one. And it's more or less from left to right. Here on the left, you can zoom in. You can highlight specific cameras if you want to have your attention to it. Later on, there will be a movie clip where the boat will be in this canal. But then there's an area where you can operate the locks, open, close. If you make a mistake, it's really costly because it will damage the lock, it will damage the ship. Both will cost you millions. And then there's other screens where they can get dynamic information, including sort of the wider area of what ships might be coming in 15 minutes towards this area. Rutger recorded professional operators while they were doing their job. And here's a little clip. I'm not a professional person, so I can't say too much about what's going on here, except that you see they're looking at the boat, what's going on. They're looking at the sort of the control areas, like, oh, are they behind? I think they need to be behind a certain area. Like, are they there? What's happening? And they go back and forth between these screens. Now, despite that, on the previous clip, I showed designated areas. What's in those designated areas is actually quite variable. You can also, definitely for these areas, you can switch what information is there, making it hard to apply regular eye tracking. You could, but it would be a lot of work. So what Rutger did is he made clips of these recordings and then showed them to experts. What do you as a human factors expert, like people who give training to the operators, what's going on here? Where are they looking? He gave them, this is the protocol that they should follow. Are they following the protocol? Those types of insights. And then he did a qualitative analysis. And the idea is that he identified 4 different types of gaze strategies, whether you are verifying what was there, whether you are gaining some overview of the scenario, whether you are anticipating something, or whether you are movement directed, placing your gaze. And I should say, these are all terms that we use. They're based sort of on the terminology that the human factors experts used. So if any of you are eye tracking experts, the way that the human factors experts, trainers use the terms might be different from how you would define it in eye tracking research. So in the paper, there's a lot of as said by the expert, this term. And there's 2 examples. So a verifying gaze, I think this was in the video clip, where the controller went back and forth between where's the ship, is the ship behind the line, sort of like on the control screen. And this is in Dutch, which most of you don't speak, maybe only me. It looks like he was checking whether the ship was past the stop area. He did that while he was already closing the gate. So while it was going on, verifying, like, did I do the right thing? They were also anticipating gazes, so like this one. While the task was going on, it looked like he was working also on something else, namely looking at the planning, which ships might be coming up, like looking at the radar images, which is actually useful in summer when there are a lot of boats in the Netherlands, and you might want to time the opening and the closing of the locks depending on the boats that are coming in. But technically, it's not, from my understanding, it's not 100% the protocol of letting one ship go through. What was nice is you could then relate those more higher level strategies to both characteristics of the fixations and the domain content, as well as the fixations and the process. So for the domain content, was looking at, well, which lock elements are being fixated on, what systems are being used. Yeah, and then there's examples, but none of us is nautic expert, I think so. And for the fixation and the processes, was it really a process that was started sequence, or was it something that was separate? And in the paper, he provides a lot of details such that other people who are in the nautical domain can use that terminology to hopefully do look at what's going on in the locks. We also looked at more general oculomotor characteristics, like the structure of fixation, whether fixation seemed structured, according to the experts, by whatever they use qualitatively as structured, or restless or restful, or very conscious or not. those we couldn't relate to a gay strategy. They didn't seem specific for specific strategies. Well, this was useful though, is to get an insight, like at least there's some consistency. There's actually all these strategies occurred with different operators, but not always in the same time. So there was both variability between operators, but also common patterns between operators. What we're doing now is we're looking at a bridge control room. The Netherlands also has a lot of bridges. Does Glasgow have a lot of bridges? Reasonable, yeah. I've seen water while I was driving in the cab. But this is a bridge control room, lots of people. This is an individual desk. Again, there's an area with CCTV screens, but it's more controlled because at each point, when you have to open a bridge, you look at one bridge. And there's some supervisory control system with which you can operate the bridge remotely. Here is again a safety aspect that you want to look at, because there have been a reasonable number of incidents. So these are very funny looking pictures, but they're actually, for the people involved, they're quite serious, and they happened. And it's not because the operators weren't doing their job, but they did happen. So there's a question like, well, what was happening to their attention? So that's what we're currently trying to solve, where I don't have data yet. But the general idea is that you can train operators to look in a structured way, where you identify areas that you have to go back and forth with. Again, there's a lot of bridge lingo here, which I'm not qualified to replicate, but in the paper it will be precise eventually. And we want to look at how people divide their attention back and forth. What Rutger did, I hope the data that we can find something, because the study is beautiful in my mind. He looked at bridge operators at their job while they're using actual bridges. Then we measured in a simulator. Then he had an intervention where some people got trained to look more structured in a more specific way than just with the hand waving. Other people didn't. Then we measured their performance. Then he measured them again, what they did. Then we measured on the job again. Then they got an intervention at their job where they got actual training that the ministry offers to the operators to look more structured. Then we want to see longitudinally whether they look more structured. So lots of rich data with a combination between simulator and real world. So far, I think with the simulated data, there we make it challenging. So there is a simulated pedestrian hidden. Statistically, it wasn't very different how often the pedestrian was seen or not seen between the structured group and the unstructured group. But now we want to know, well, did the structured group do what they were told? Did they actually look structured? And were they then, maybe on the instances where they did look, were they a bit faster? And that does seem to be the case. Okay, so I've talked about the automotive domain and the bridges, right? I had also most data to show. Briefly, two other topics, such that if there's any of you interested later, we can talk more about that. Floor is a relatively new PhD student. This is the city center of Utrecht, an area where people that go to campus, they pass this either on bike or on car, or by bus typically. And the city wants to redesign this space. And that's the practical question. How do we design that market area? And in part of their practical application, they use urban digital twins. So these are simulations of pedestrian flow through a crowd. Now, the problem is those urban digital twins are actually quite advanced. So the company we work with, UCrowds, they also simulate pedestrian flow at King's Cross Station and St. Pancras in London to real-time adapt navigation routes there. They've applied it for large sports events like the Tour de France. But in some sense, the characteristics of the pedestrian is a dot or a vector. You're going from here or here with some characteristics, and we're trying to see if we can get a bit more of the psychology in it. And as a first, right. We just got this was other project with a massive group of people where somehow we managed to be on the same page with 25 on the position of urban digital twins. And one of the main takeaways was it's useful to think about the people. So that's coming out. I'm quite proud that that paper happened. I wasn't the lead, that was Judith Verstegen on geosciences. Anyway, there's a need here for putting more information on the human in those digital twins. What Floor did so far is your fake bicycle driving. So now you're on your cycle and you're driving through Utrecht. This is the simulation of Utrecht. That's the Dome Tower. And now the question is, someone's crossing the street, do you stop or do you go? What do you do? I think most of you would stop. But there's also scenarios where it's maybe more ambiguous. And Floor manipulated various things. How fast am I driving as a cyclist and from what distance? Do I have a dedicated lane? Because that's something you could redesign in the environment. And how busy is it with pedestrians? And how does that change my willingness to stop or to go? Which so far it seems to show that mostly the pedestrian density influences the behavior, at least in these experiments. And the road structure was more variable. Sometimes it had an effect, sometimes it didn't, so I don't claim too much about that. What we want to do next is with experiments like this, where you have a stop or go, you can put them in more formal simulations, the drift diffusion models. We want to make that, but Floor was actually, yesterday, she was also on the street. We're now observing, oh yes, good, yes, sorry, yeah. She was observing on the street how people are crossing the streets. So we also want to get qualitative insights of what people actually do in the behavior, because the experiment is, of course, extremely controlled and not the real world. We then want to tie them together at and describe it in such a way, the Floor is an engineer by training, that it can be put in these digital twins. Last project is the train domain. You've seen this guy already because he was our fake train operator or train planner from the previous picture. This is with the Dutch Railroad. And they have this practical question of if AI is needed to, given the increased demands of trains on a finite set of tracks in a very tiny country, we might want to use AI. But do the planners even trust it? Due to the AI Act in Europe, the human operator needs to check plans, needs to be secure with to what degree do they trust it? So more generally, how do we trust proposals by AI versus by humans? We're not there yet with testing actual train plans. We were quite close to testing that, and then the train operator said not possible now. So we came up with a game, which is a bin packing game, which is used a lot in computer science because it has a characteristic of a combinatorial optimization problem. So there's multiple possibilities of solving it. The idea is you have a set of resources, here blocks, but in the real world it could be trains, and they have to be redirected to a finite amount of space. How much space do you need? Well, maybe it doesn't fit in one area, so you use two. And there's also other ways of solving it. Oops, which what do you do there? What we did in that context is we presented solutions, which we only told this is solved by by a human, or it's solved by an AI agent, but it was all the same stimuli solved by the same person. How likely are you to trust it? And we compared a student population so far. Next month, we hope to work with professional planners from the rail companies. The experts, relative experts, computer science undergraduates, who've known about NP completeness, for example, and who've seen some of these optimization steps, they typically rated these AI solutions higher than those by the humans. But if there was also a bad solution in between, and once that had happened, they continued rating badly so far. Whereas the relative non-experts, these were the psychology students and social sciences, they tended to rate the AI and the human solutions, which were really the same. They tended to rate them the same, but when they saw a bad solution, when they saw a bad solution of the AI, it didn't change their judgment too much. So we're quite curious to see whether people who are maybe not trained in computer science, but who have on-the-job experience with these types of training, like the train planners, whether that's the same. So yeah, so that's the next step. I'm out of time. So summary. Automation and AI changes human behavior and mobility. I hope I didn't say a lot new there. This you already knew, but maybe I've given you some new mobility examples. And one of the reasons is due to this irony of automation, that AI or automation changes how we do tasks, and also in unintended ways or unanticipated ways. So therefore, there's a reason to try to predict the future based on really fundamental theories of systems, but in my case, as someone at the psychology department, theories of humans. What do we know in general about human attention and behavior? And to also do really critical tests, including on the job, so with these bridge operators or with the train operators. And I've shown you these various examples of human automation interaction, which varied in their methodology and domain. So from cars, bridges, urban planning, and trains, and the PhD students did most of the work. That's what I wanted to say. Thank you. Maybe I'll go back to this slide because that's the names of the people who did the work.
So we have some time for a question or two.
But one question that unfortunately we have to go because I have another meeting, but I go back to the first study you presented that has to do with self-driving cars, etc. Or in the case dealing with systems that are heavily automated, right? To the point that they have a certain degree of autonomy. So the algorithms, they are quite predictable, you can expect it to do more or less what you will do.
Yep.
But there is a degree of autonomy that comes from say unexpected behaviors or possibility of errors or factors that you don't see as a person, but the car can get. Do you think, for example, that learning from how people, for example, ride a horse, so highly skilled people will basically deal with an animal that roughly is an autonomous agent, so training becomes extremely predictable, but still.
Yep.
It is an autonomous agent that can have unpredictable behavior. You need to establish a relationship. That's how typically these people put it, right? Do you think that could be a way to address the problems you mentioned of establishing this trade-off between yes, the car does the job, but still be there?
Yeah. So maybe for the online folks. So the question is about in situations with higher automation, whether we can take inspiration from interaction with animals like horses. In fact, that has been done. So there's the H metaphor, the horse metaphor. And the idea is, one of the insights it's been used for is to at least conceptually think of loose rein and tight rein. So do you take tight control of the horse while the horse still does the actions, but you're really in control? I'm not a horse rider myself. Or more loose, where you let it go, but occasionally in subtle movements, maybe you steer by. That's what I've been told. I believe there's some limitations to it, but I can't bring them back to mind at the moment. One limitation I think that has been said in the literature, but again, I'm not 100% sure, it has to do with a horse. Because it's an animal, it might not want to die. So it will do a couple of things it will definitely not do, independent of how you steer it. And that's where at least some of the metaphor breaks for the car, philosophically. But it's very useful indeed to think of it also in terms of this. How do you collaborate? So I do like the idea of the horse and the horse rider are definitely a team, which is a vision that has been proposed in this literature, and I think some of that goes back also to the 80s. So it's been around. It's around again to think about teams, but sometimes we, including me, think naively more as the car is doing more things or I'm doing more things. Yeah.
Thank you.
You're welcome.
And what was the name for the term for the back and forth between the question?
The back and forth interleaving.
To what extent do you think people should be allowed to, a system should allow a person to interleave rather than just producing alerts which will ruin their task, but guarantee or make more likely they will behave safely?
I'm not a legislator, so I probably shouldn't be in charge of what's allowed. Because that's a question, when should it be allowed? I would say, I think that scenario needs more attention. So the bulk of the research so far is about instant alerts, or more or less instant alerts, 5 to 8 seconds typically. And the question is, if it's about 5 to 8 seconds, why doesn't the system itself do something maybe? If it's really this last minute alert, whereas some, we've done another, I just didn't show that, but another study where we had pre-alerts that warned you 20 seconds up front. Then we always got the question, will this work? And it actually, or could it be implemented eventually? And I think there are lots of systems in place that could allow for those alerts where you have, for example, crowdsourcing of, hey, I've detected an object on the road, or there's a traffic jam ahead. So some things that are further in the future could be early alerted. And in those cases, thinking about how to design for early alerts will work. But given that the world is highly dynamic, I'm certain there will be scenarios that you can't warn more than 10 seconds up front. But if you can, I think that's something to consider, given that to humans, if this automated system is highly automated, highly reliable, they might want to consider, they might be more interested in doing other things than immediately grabbing the wheel. Or if they do want to grab the wheel, they might want more time to orient themselves on what's happening in the environment. Yeah.
Because some of the data suggested that people might have to be saved from themselves. That will, the instinct is to finish what they're doing.
Yeah.
Get that later.
Yes,
But maybe they can
that's
do
also
that
true.
more
That-
quickly.
yeah.
I guess that's going to be look at the conveying emergency or something.
Yeah. Yeah. Yeah.
If human nature.
Yeah. Yeah. Yeah, humans often need to be saved from themselves and their bad habits. Yes, I agree.
It's unfortunately we ran out of time, but Chris is still around here today and tomorrow. There hopefully is cake, coffee, and tea outside.
Oh,
So yeah, so can we continue the discussions? Yeah, so let's thanks. Thank you so much. This was very nice talk. Very interesting work.
Good.
Unfortunately, I need to go to a couple of meetings, but yeah, I'm sure there are people around.
Can you help me with getting the Zoom control again? Because now I did, stop sharing.
Oh, yeah.
Because I lost my Zoom bar.
It's recorded on the cloud, so.
Oh, and you did the recording.
So you just, yeah.
And-